Dynamic programming is what we've been talking about. And I think we've been using the example of making change with coins. So, okay, so just to keep us, get us swapped back in, overall, we're looking at two techniques, memoizing and its older brother, dynamic programming, older sibling. Older, more talented sibling. Anyway, we're looking at these two related things here, and we've seen an example of memoizing with the coins problem. So again, what was the coins problem? I want to make change. I have a certain set of values of coins, say, one a penny, a threepence, and a quadrupence, or something like that. If I have these four values, then it's not obvious how to find the fewest number of coins to give change. Okay. But it's obvious how to write a program that searches through all combinations. And that way of searching is say, hey, go ahead, and if my n is, I need to make 50, n is 57. I need to get 57 cents away in change. Well, look at the following ways of doing it. I can give away for every coin C, whether it's a penny or a threepence or a quadrupence, I can say, hey, use one coin, use a penny, which that's one coin, and then say, hey, give 56 cents optimally. Or that's one way of doing it. Another way of doing it would be saying, hey, I'm going to give one coin back that's a threepence, and I'll give 54 cents. Or I'll give one coin back that's a 4-cent piece, and I'll have make perfect change for 53 cents. Look at those three choices. There's three different ways of doing that. You can give away, just make one choice. What you give one coin, recur to find the other solution, and then say, hey, take the best of those three. At this point, I had three possible answers, and so let's take the minimum out of those three and keep track of which one took the fewest coins so far, and that's going to be my answer. What we saw, we sort of drew out the decision tree, the execution tree of doing this for a small value of coins of 6 or something like that, and saw that there were many repeated subproblems. We were computing coins of 3 like several different times, and computing coins of 3 involved computing each of those calls to coins of 3 involved calls to coins of 2 and coins of 0, which is a base case, but and so on. So yeah, coins of 6 would have end up with many calls to coins of 2. Okay, and so yeah, we're repeating that work. So what was the obvious solution? Memoize it. Hey, just make a note every time you call a function. Hey, I was called with the input of 3, and here's the answer I came up with. And if anybody calls me in the future for coins of 3, I'm not going to recompute it. I'm just going to look up that I have it written down right here. I've memoized it. I have a little memo saying, hey, coins of 3 is going to return 3 or whatever it returns, 1, I guess. And it builds up. Later somebody wants to know coins of 57, and that involves a lot of calls to coins of 23 way down the chain. But after the first time of computing coins of 23, we write down what the answer is and never do the work of coins of 23 again. We only do it once. And that turned this, we saw running the program. So I'm looking at the file coins.py, and also on the lectures page, this coins.python is linked on the lectures page, and so is, I believe, dynamic programming.txt. Is that what we called it? Yeah. So I started there, and then I switched over to giving actual code that actually ran. So, okay. So we had coins that was simple, mindless. The mathematical definitions, like, hey, just try one coin each, decrement the total by however much you gave back, and solve this sub-problem. Add 1, that's how many coins you have total. Look at the minimum over all choices of the first coin you give away. And will definitely give the answer, but had that repeated subproblems, ran really slow. We saw that it ran okay up to about 35 or so, I think. And then it started really bogging down. And every one took about 3 times longer than the one before. And so I think coins of 34 coins of 32 started being noticeable. Coins of 34 was slow. Coins of 36 was painful. And coins of 38, you start, waiting for 30 or 40 minutes. So memoizing, that was our first version. How did we memoize it? Pretty easy. Kept an array called answers. Okay, started as an empty array. We'll initialize it. Hey, and we took the same code we had before. So here's what I want to point out is that in some sense, this is going to be a very mindless change. Memoizing a program is a mindless change. Keep my little memo pad on the side, answers, initialize it to be empty. The first thing you do when you're called, hey, do I already have it memoized? That's this first line, this line up here, okay? If it's already in my answers, then just return answers. If it wasn't in answers, then do this code, and instead of returning at each point through, I go ahead and record so everywhere it had a return statement before, I instead assign to my answers array. Okay. I need to be sure to change the recursive call to be this new function that's doing the memoizing. So I did a copy and paste, but I had to change the name of this function. And this now ran in large inputs, 60, 70, 80 at least, didn't even reach 1 millisecond, which was our clock, our timing resolution. So yeah, this runs really great. Okay, we can go and look, by the way, at the runtime of these. We'll think about what the runtime is, the analysis. Okay, what else did we have? After we did this, we realized, hey, how did this answer arrays get filled in? In some sense, I feel like it's filled in top down, in that the first thing I try to find, I call a coins memo of 57. The first thing I'm trying to do is look at answers of 57, and it's not in there originally. So I go and start computing, okay? In trying to fill answers of 57, I'm going to call coins memo of 56, 54, and 53, okay? Each of those, so coins memo of 57 makes a call to coins memo of 53. Coins memo of 53 is going to not going to be there, so it makes a recursive call to coins memo of 49, and which call 40, what is that, go down by 4 each time, 45, and then 41, and so on. And finally, we'll get down to coins of 1, and then we can't use a 4 cent or a 3 cent, but we can do a 1 cent. We fill in coins of 0, then we fill in coins of 1. That goes back and says, okay, I'm back to looking at coins of 5. And I computed coins of 1. I also need to look at coins of 2 and coins of 4. So I recur on those two. And but if you look at how I fill in that array coins, it's kind of driven from the top. So that starting at 57 and trying to fill in stuff from there. And for some reason, coins of 23 never came up as as part of something that plays into the answer. I would never bother computing coins of 23. I would never call coins of 23. So yeah, that's nice. So top down. Doing say we could also do it bottom up. Bottom up is saying, hey, I'm going to make my array answers start as an empty array. I know in Python I'm using a dictionary here, but imagine that's an array of size. Hey, you're calling coins memoized bottom up, BU for bottom up, of 57. Make an array that's 57 long, and start filling in element 0 of the array. Then fill in element 1, 2, 3, 4, 5. So when you're coming along, you're saying, hey, I want to fill in element 6 of this array. It's pretty easy, because when you want to fill in element 6, you can just look back. You know that in your array, you already have filled in everything smaller because you're working bottom up. So, hey, what is coins of 6? I can look at in my array, I can look at the optimal answer for 5 and 6 minus 3 and 6 minus 4. Okay, and later I have 0 through 16 filled up. I'm trying to figure out what is coins of 17. Well, coins of 17 only I can give the optimal answer if I know the answer the best answer to coins of 16, coins of 17 minus 3, and coins of 17 minus 4. If I know those three answers, I can figure out coins of 17 and record that answer. Okay, so here I can just go ahead. I don't even need to make a recursive call. I just flat out look in the array because I know it's in the array. I don't need to go and recur and have an if statement. If it's in the array, then blah, blah, blah. I know it's in the array because I'm filling it bottom up. Okay. So that's great. That's basically the same as top down. It might be a little worse, I guess, because top down, like I said, might skip over. So if you never need to know coins of 23 for whatever reason, if when you fold back on the numbers, it never happens to hit 23, top down will never compute coins of 23, but bottom up will. Okay. So is that where we got to? I think that's where we got to. So now that's memoizing. Memoizing, just keep a table of previous values. Dynamic programming. Now this sounds cool. It's kind of maybe a little bit of a buzzword, but dynamic programming is simply saying, hey, think of that bottom up solution we came across. I wanted to know coins of 57. So I had made an array that was 57 long and I filled it up. But as I'm filling it up, great, I'm coming along and I'm trying to fill in coins of 17. And I know that coins of everything less than that's already been filled in, great. But out of when I'm filling in coins of 17, which cells do I need to refer to? Only ones within the previous 4 slots, okay? Because my largest coin size was 4, a 4-cent coin. So, I didn't really need to keep when I'm trying to get coins of 53. I'm going bottom up. I'm filling in coins of 17. It's nice to know that I have the previous things all filled in, but I don't need all 17 things. I only need to keep the last few. And once I've filled in coins of 17 and I'm trying to fill in coins of 18, I can only keep track of the previous 4. I can throw away. In fact, I don't need to keep track of coins 1 through 14 or something like that. By the time I've reached and trying to fill in coins of 18. In fact, by the time I'm getting up to coins of 52, I'm almost done with coins of 57. I fill it up, I'm up to coins of 52. I don't need to keep coins of 1 through 48-ish. Because why? To fill in coins of 52, I only need to know the 4 previous array cells, and that's all. This is the observation of dynamic programming. Memoizing made me keep an array, and now imagine I was looking at coins of 1 million, okay? Dynamic programming made me keep an array of size, or memoizing made me keep an array of size 1 million. But I don't need an array of size 1 million. I can get by the whole thing with an array of size 4. If I can keep that array of size 4 to be a little sliding window of exactly, imagine filling in that array, but you're only keeping track of a little window of size 4, computing the next one, and then sliding your window over, letting one thing fall off, and your new value you just computed goes into the top of that window. You can get, you don't need an array of size 1 million, you can do it with an array of size 4. Running time stayed the same. I'm still computing coins of 0, then coins of 1, then coins of 2, coins of 3, all the way up to coins of 57, all the way up to coins of 1 million. Running time is the same. It's simply dynamic programming is a hack to let me keep that table of memoized results, keep that table small. And this is not an automatic mechanical thing to do. You need to be clever. You need to think about, hey, do I really need to know all the previous values, all my memoized values, or can I get by with just keeping some of the memoized values? And the way I'm filling it in, bottom to top, is letting me be clever and say, hey, I can do some reasoning and realize I only need, in this case, I only need 4 of those values. It's not an automatic compiler. I'm not going to think about writing some code that automatically tries to take a recursive program and make a dynamic programming version. I can automatically make a memoized version, but a dynamic programming version requires cleverness, okay? So, and I have the actual code here. Here's coins DP for dynamic programming. Same purpose statement, by the way. Why doesn't my purpose statement include how I solved the problem, because that is not the point of a purpose statement. Your purpose statement should just sort of say, what does the function return? If you have comments about how it works, put those comments inside the function. Think about math.square root. If you go to the math documentation for math.square root, maybe you're wondering if you're allowed to put in 0, or could you put in a negative number? Are those things allowed, or what? You don't want to read a paragraph about, hey, we use Newton's method with a incremental step size of 1 times 10 to the minus 35 with blah, blah, blah. No, you don't care about you don't care about how it computes the square root. If you do, go look at the source code and look at the comments inside the source code. But your purpose statement is just, hey, this function returns the square root, or in this case, coins dp returns the number of coins needed to make n cents of change. Okay. So look at this dynamic programming variant. Parts of it look the same. This part looks the same as that bottom-up version, okay? In that we went ahead and we always looked at 1 plus, and then we looked up a previous looked up some previous value. I have an array answers here. The index is going to be tricky. Here's what we're going to do. I'm just going to say I'm going to keep an array of size 4. And again, why 4? Because our coin values were 1, 3, and 4. 4 was the biggest coin size. There we are, 1, 3, and 4. So one test. 1, 2, 3. Yeah, 1, 3, and 4. So I'm going to keep an array, and my array is only going to have 4 things in it. And as my value I loops, as I goes up, starting from 0, 1, 2, 3, 4, up to like 57, up to all the way up to 1,000,000, I is going to be the value that I'm trying computing right now. I'm just going to keep track of, I only need to know, to compute coins of I only need to know these 4 numbers, okay? Actually, I don't even need to know this number, but when I increment I by 1, I'm going to need to know so when I'm computing coins of 57, I don't really care about coins of 55. But in a moment, when I get to coins of 58, I will care about coins of 55. So that's why I need to know, I'm going to keep track of all 4 of these values. Okay. So when I is 57, yeah, I'm going to have an array that has coins of 53, 54, 55, and 56, and that will let me compute coins of 57. How many people use Python much here? Use it a little bit? You can raise your hand in the, do a little participants and raise hand thing too. In fact, I can pull up my participants buffer. So Python has one little cute feature in that it allows you to have your array indices. If your array index is too big, you'll get an array index out of bounds error, and if it's way too small. But it lets you use negative numbers, small negative numbers, and it wraps around. So if you have an array with indices 0, 1, 2, 3, I can go ahead and talk about answers 0 and answers of 4. If I try to go and access answers of -1, okay, so 0, so 3, 2, 1, 0. If I try to go and access answers of -1, it wraps around and it comes back to answers of 3. Okay, so in Python, you can actually say answers of -1 and it will get you the one most previous back. I'm just going to use that cute little fact about Python to sort of say, hey, I need to keep track of coins of I -1, I -2, I -3, I -4. I'll store those in the locations, answers of -1, -2, -3, -4. So I'm going to use negative indices for my array just because it's easy for me to remember this relation. Okay. And that's what I'm doing here. C is my coin value, either 1, 3, or 4. And I look up answers of -1, answers of -3, or answers of -4. Okay. And that goes back to that many cents less. Okay. So in Java, I'd have to write a little bit different. I wouldn't use the negative indices. I guess I'd just replace wherever I say -1, I'd say that plus 4. So I'd say -C plus 4. So I'd say 4 minus C. Okay. So that'd be the same code in Java, I guess. Anyway, yeah, this loop looks the same, except that my index is only going to index one of the 4 most recent places, and I'm only going to keep the most recent 4. So what do I need to do? The one other thing here is like, okay, great. I'm computing coins of 57. I happen to have my array with coins of 57 minus 1, minus 57 minus 2, 57 minus 3, 57 minus 4. Now I increment I, and so I need to take this array of 4, and I want to get these 4 values. So I want to basically take these 3 values. I think what my code does is I say, hey, take these 3 values, make a new array that has those 3 at the beginning. Okay, has those 3, and then the top value, replace that top value. So basically shift them over and put my new result in here, which is what this is Python for. Answers of 1 colon, that's an array slice that says, hey, take the whole array starting from index 1 onward. Okay, so I have this array of size 4. Hey, take from index 1 onward, grab that, make that the new start of my array, and then append it to an array of size 1 that contains my new number, fewest so far. So you don't need to understand the Python aspect of that, but I don't know, the Python designers made it read pretty easy once you get this idea down. So yeah, this little getting to use negative indices and getting to use this array slice works out okay. By the way, if you think about it, I have a little comment here. Every iteration of I, I'm actually copying over my array. I'm just on the array of size 4. But if my coin value, if I had 27 different types of coins, then that'd be an array of size 27. At every step, I'm copying 27 things over. Probably smarter than copying them over is to sort of use it as a circular buffer and rewrite elements of the array without doing them. That would make this index be a little bit more intricate. I have to do a circular formula. I'd have to say like I minus C mod the size or something like that. And that's probably all I need to change. But so in real code, I'd actually probably even sort of optimize this. This is an array copy here, which if your array size 4 is not so bad, but even so, we can optimize that. Okay. I get through there. When I finish, I has gone 1 beyond what I want it to be. I incremented I and it was past n, so I minus 1 is what I want, which is the answers. And I wrote this code, and I'm like, does this really work? I mean, I'm doing this fancy stuff here. I have this here. It's not clear I got it right. Yeah, good thing I have those test cases all these ready to run, and it turns out it did run fine. I was not sure at all until I ran those test cases and they passed, but let me tell you. Okay. Oh, chat window disappeared. There we are. Okay. Questions or thoughts on the coins problem as our poster child for memoizing and dynamic programming? We're going to work through one more example, okay, of memoizing and dynamic programming. Talk through it at least, if not show the code. But does that kind of make sense? The idea of memoizing is easy. And by the way, I should point out, going back to my dynamic programming page here, going down a ways, yeah, let's step back and just look at a few things. First of all, the term memoize means remember the value for previous input. And somewhere I have a note in here saying that, you don't need to have a recursive formula that can benefit from memoizing. Say just string append. You have a function string append. That's a very straightforward function, but if you're appending maybe long strings a lot, it can take a while. Hey, why not every time somebody calls string append, I'm going to go and remember the 2 strings that's passed and remember what the result was, and then not have to compute it and loop over characters. If anybody asks me to string append the same thing in the future, I can just look it up in my memoized table. That's probably not going to be too useful because most programs, even when they call string append, don't call them on the same strings over and over and over again. But if they do, if you have a situation where you think string append is going to get called a lot, and for whatever reasons, it's being called on maybe strings that are very long, and there's only a few hundred different strings, and so there's only maybe a few hundred square different pairs of strings that are commonly called with. And so, yeah, maybe memoizing string append can be a win. Okay. In fact, there's another function that does memoizing. It's called your browser. What does that mean? Your browser memoizes? Hey, what happens if you go to a website that you've just visited yesterday? Does it have to recompute? Does it have to go and make a query all the way to that page? No, it might cache the page. Caching is just memoizing, right? So page lookup on the web, it can be memoized.
I know smartphones do that a lot with like apps where they'll keep a lot of the, like on Facebook, they'll keep a lot of the posts that you already saw and like keep them preloaded.
Exactly, yeah. So that's sort of, if it's a pretty obvious thing to try to do, to just sort of say, hey, stuff that's going to be asked for again in the future, just keep it around, keep it local. Remember the result of asking for that, my previous 100 posts. And that's the same idea of memoizing. By the way, another thing, the way I wrote even that coins memoizing problem, if you called coins of 57 and got some answer, and then later, maybe 2 days later, your program's still running and it calls coins of 41. Hey, that memoized array is still around, and coins of 41 will just return instantly, even though it's a whole new top level call. So memoizing, again, doesn't just optimize within the one, the call made from outside. Repeated calls from outside can end up getting memoized too. So, okay. Usually when people say memoizing, they mean just what we talked about. But if you step back, caching and multiple top level calls are all sort of memoizing and doing that same thing. So if that's memoizing, what is dynamic programming? The thing that we did different in dynamic programming, we computed the memoized table bottom up. That was sort of okay, or we thought about doing that, but then we realized, hey, if I compute it bottom up, I don't need to keep the whole table. I can just keep a little sliver of it. In this case, the last 4 items was our example there. That's the dynamic programming optimization. Does it make your program run faster? No. Does it make it use less memory than the memoized? It's not faster than the memoized. Does it use less memory than the memoized? Heck yeah, from 1 million items of extra memory down to 4 items of extra memory. So what is a recipe? Remember that premature optimization is the root of all evil. Some say, I don't know about all evil, but a heck of a lot of evil, yeah. So when you need to write a function that follows, if there's some formula that gives you the result you want to, just implement that formula. If it's a recursive formula, you'll get a recursive code, that's fine. Write it, run it, make your test cases, see if it works. It's going to work if it's the right formula and you implement it. You might run into the fact that it runs too slowly, and it might be running too slowly because you have that repeated subproblem issue, okay? So, but notice that, hey, if your simple version runs just fine, great, don't bother optimizing it, okay? But if it runs too slow, then try memoizing. Why? Memoizing is a rote mechanical transformation you apply. You just sort of keep your array of answers, and you, before you actually do the work, you just look up to see if the answer is there. Okay. And now if it runs fast enough, great, you're done. Well, I don't say if it runs fast enough, I say if it runs fine, then you're done. Okay. Because it might run fast enough, but take too much memory. Okay. So if it runs too slow, you're also done. Because going from memoized to a dynamic programming answer doesn't really speed you up. Okay. So if it's running too slow, then gosh, I don't have a good algorithm to solve problems of this instance. Maybe I need a whole nother different algorithm. But if it runs fast enough, but it's just chewing up a huge amount of memory, then go and try dynamic programming. This requires cleverness. See if you can figure out a way to, take that memoized table, build it bottom up, and observe if you can somehow be clever and only need to keep around a portion of that table that you're building bottom up. Okay. So that's the thing is, hey, write naive code and it might be good enough. If it is, run it and test it and benchmark it, and you might be done right there. Don't waste your time with anything else. If it's too slow, try memoizing. You still have your test cases, so you can check all those, and you might be done at that point. You might be done either because it runs fine, or you might be done because it runs too slowly and dynamic programming doesn't help. If you're in this little window though, hey, it runs fast enough, but uses a huge old chunk of memory, and I can't do that in general when I'm running on the web server. When I push my code live, I can't take that much memory. Then consider dynamic programming. And by the way, I have a little asterisk here. If it takes too much memory, using too much memory ends up costing you time, right? Why you have to allocate the memory, you have to maybe be moving it around. If you fill up your physical memory, you might start swapping out to virtual memory, out to the disk, or even just out of a cache page. The more and more cache hits you get, that's going to slow you down. So there is a time slowdown that's not related to the algorithm. It's just related to your memory. If you're asking for memory and you don't happen to ask for it in a way that your hardware likes it when you request memory that's a small amount of memory that's all together. You start requesting memory from all over the place. Yeah, there is that slowdown. That slowdown can be alleviated if you use less memory, of course. So, by the way, if I look at the runtime, the asymptotic runtime of an algorithm, why do we never talk about memory usage and the fact that paging takes so much more time? Oh, because that's a constant factor. Hey, every memory access takes 1,000 times slower than before, or 1,000 times longer than if I were somehow clever and using the really fast core memory. Hey, a constant factor of 1,000 is a constant factor. My memory speed, this asymptotic analysis, is independent of memory speed. Why? Because we ignore that constant factor of how long a single memory access takes. So, okay. By the way, the term dynamic programming, I have a link on here in the notes in this dynamic programming text that's linked on the lectures page. I have a little link to a Wikipedia thing, has a little quote from Bellman, has a name on another famous result. He was a researcher, and he has a funny quote about why that term dynamic programming. But it's worth mentioning that like dynamic programming, that's kind of a loaded term, and it stems from the fact that, first of all, programming was actually meaning planning. Like, hey, I'm in management science, and I have a certain set of workers and set of constraints and set of tools and shipping constraints. I want to find the best way to assign my workers and place the orders, and I have constraints in my cash flow. I want to find the best plan to most efficiently do whatever I want to do, and that's called programming. That's sort of the sense of the word programming that predates computers somewhat. And linear programming is another. It comes from that sense and is unrelated to programming of computer, just making a plan. And so Billman was actually doing research, and he coined the term dynamic programming. He was using programming in that sense. Okay. And why dynamic? Because you're sort of, as you're running, you change your idea of what the best thing is, and you update your idea based on this thing. Partly he chose it as a buzzword, and he talks about why in that little anecdote. But, okay. Before we go and look at one more example, well, I want to look at the runtime of this coins problem. I will say too that I used Python dictionaries for memoizing. All the examples you'll find in the book and on Wikipedia and online always talk about using an array. Yeah, if you call a function and the input is a number, like coins of 57, then really I want an array of size 57 to memoize. If I want to memoize or do dynamic programming, I have this array going on. And in fact, if I have all small numbers, if I use a hash table, but my keys are 4, what do you think 4 hashes to, by the way, or 57? What's 57 hash to in a lot of languages? 57. Okay, so if you think about how a hash table works, if your keys to a hash table are all small integers, they're going to sort of, it's an array. You're going to have just an array, just be using it as if it's an array. So, so I use a hash table. If my keys are integers, that's kind of the same thing. But if the inputs to a problem are strings, or if the inputs to a problem are other objects entirely, then this memoizing technique still works with a hash table. And so that's why I just use hash table. I think of it as memoizing, say, hey, memoize whatever my inputs were for any function in the world, just memoize the inputs. But you're right, when you look on the web and they talk about memoizing and or dynamic programming, they always use integers, and they always use an array of integers. So okay. Let's look at the runtime of this coins problem. Okay, what is the runtime of this coins problem? Memoized, dynamic programming version. Let's look at the runtime of the memo. Well, I'll tell you right now what was the runtime of the original version that said, hey, what is coins of 57? And it called coins of 54 and 53 and 56. And the coins of 56 called coins of 53, and both times I called coins of 53, they both called, each of them called a bunch of coins to calls to coins of 51, and each of those calls to coins of 51. There's now like 4 of them or more, or 6. Each of those called coins of 50, and there was like now 8 calls to coins of 50. And yeah, there was a lot of those, all those repeated calls, and they occurred exponentially often. So how long was the original runtime? 2 the end. It was at least 2 to the end. It was actually more like 3 to the end or 4 to the end. I'm not quite sure how many. Is probably 3 to the end, probably close to 3 to the end. I'm saying big omega because I'm saying it was at least 2 to the end. It was actually, I think, even asymptotically bigger than 2 to the end. So I'll say big omega there. I think, yeah, the original runtime was worse than 2 to the end, which is awful. Remember that table we filled in on the very first homework about number of seconds, how big n can be on a modern processor before you get older, need more than the age of the universe to compute your answer? Yeah, if n is 100, you're starting to press that boundary, or less than 100. Yeah, we don't like algorithms with time 2 to the n. And small values of n make it useless. What was the memoized runtime? So let's go look at the memoized code. Here's the memoized code. Do we have any loops going on in here? We have an if statement, an if statement. Oh, this looks like a loop here. Okay, so we have this loop going on. Maybe we should even look at the dynamic programming version. That's maybe even more clear. Let's do that. Let's look at the dynamic programming version. Do I have any loops going on here? I have 2 of them, right? Here's one loop. I was filling it bottom up. So he called coins of 57. I started filling up my table from 1 to 57. So I had a loop that goes n times. How much time does each individual loop take? My total running time is going to be n times however much this loop takes. Now this might be different, but inside this loop, we had another loop. Here's a for every C in vowels. So vowels was the number of coins I have, which was, I think, just 3. I had 3 different coin values 1, 3, and 4. So I only looped over 3 things. But if I had 100 coins, this inner loop would take 100 steps. Okay. So what is the overall running time for coins? I have an outer loop that I make n calls to, and an inner loop that is the number of coins that I have. So what is the running time? dynamic programming running time. It's going to be big theta of n times v. N is input, v is number of coins. Okay, so I had my variable vowels is the size of vowels, VALS. Okay, yeah, that's much better. Okay, we like n times v. Okay, and the memoized runtime, turns out the code is not as clear if you look at this code, because yeah, we have these recursive calls, but if you look at the recursive calls that go back, really, it does some work once and then caches it and then never does more. So any one recursive call looped over 3 other things and then was never really called again because it got memoized. So it has the same the same asymptotic runtime. What's going on here? Just copy paste this old-fashioned way. Okay. So that's good to note. Other programs that run, and maybe next time I was thinking about this, next time I teach this class, maybe instead of the coins problem, I'd use a related problem. And there's several different related problems, but yeah, there's one called the rod cutting problem, which I might use. In that case, the number of recursive calls you make inside the loop could be up to n. And so you might get an order n squared algorithm. Okay, so it's not too uncommon. Here we got n times v, which is kind of linear if you hold v fixed. That's linear in n. So that's kind of neat. So we went from exponential down to linear. It may not always be linear, might well be n squared or n cubed or something like that. Okay. So next problem. Any questions or thoughts, by the way? Thoughts like, hey, Barlin, so nice outside, can we go outside? Oh, a cloud just passed over the sun for me, so it's not so warm outside, so no, you can't. Okay. Failing any questions, let's go ahead and we're going to look at a different problem, matrix multiplication. Okay. And the idea of if I need to multiply a bunch of matrices in a row, you might say, Barlin, what sort of problem is that? Who needs to multiply a bunch of matrices in a row? Certainly graphics processors are often multiplying matrices. There it's usually square, so it's not an issue, but and we'll see why it's an issue in a second. How long does it take to memorize? I'm gonna go over to my scratch paper here. How long does it take to multiply a matrix that is A by B with another matrix that is B by C? So remember how matrix multiplication works. Okay, so I'm gonna switch over to my webcam user here, iBarl and iPhone. And I'm gonna remember how matrix multiplication works. So if I have a matrix that is A by B, okay, maybe it's a 3 over 2 down or something like that, okay? And I have different numbers in here. Okay, and I want to multiply this by another matrix. What is the shape of the other matrix? It turns out as long as it has this one has 2 rows. If I have a matrix that has 2 columns, then we're okay. So I'm going to look at a 2 by 4 matrix. Okay, or in general, a B wide, it has to, the height of here has to match the width of this one. I think I got that right. And I'll call the height C or whatever in general, but maybe this is a 2 by 4. So negative 2, 0, 1. Try to keep these numbers full. 1, 0, 3, negative 1, and 1, 1. Sure. What is this? What happens if you multiply these 2 matrices? Let's go ahead and I'll go down here. My answer, it turns out, is going to be A by C matrix. It's going to be 3 by 4. If I do this, I think, if I got this right. So it's going to be A and C. So it's going to be actually, in this case, a big matrix. Why is that? Because, hey, how do I compute the location of the upper left, location 1, 1? Take row 1 and column 1 and do a dot product. 3 times, -2, -6 plus 1 plus 18. -6 plus 1 plus 18 is 13. Okay, so that location is 13. What's going to go in this location here? Row 1, column 2. Take row 1 of the first matrix, take column 2 of this, and take the dot product. Wait a minute, I goofed up already, didn't I? What am I doing wrong? I need to have the dimension, the second dimension line up. Is that right? I'm saying B is the one matching up. Yeah, I think I got these swapped. I'm doing the matrix, the multiplication of the wrong order. I should take this times that. No problem. So, sorry about that. To multiply this, it's kind of a question of what you call a row and what you call a column in some sense. If I multiply these, I'm going to get an array that is now the row 1. Wait, that's still. I'm confused. I've confused myself. I want the 2 to be in common. And now I'll just transpose things. Gosh, you guys, anybody want to help me out here? You guys know how to multiply matrices, right? Many of you have had calc. Isn't calc 2 all linear algebra? Matrix transformations? Yeah, yeah, so I think let me try one more time. If I don't get it, then I'll punt on that. I want to say, actually, we're going to go to some notes made already, and those will have it done for us. Have the, so the 2 shape, I need to join up, the 2's are what you need to have in common. So I need the, yeah, no, this is, the second one's right. If I call it row and column. Okay, yeah, I'm sorry, just a little braino there. What is the upper left corner going to be? Take, if it's the first row, first column, take the first row of the first table and the first column of the second table. So -6 plus 0, so I get -6. Okay. What is the second row, first column? Take the second row and the first column. 1 times 3 plus 0 times -2. You can see why I like zeros in this table here, right? So 3. What is this location? This is going to be first row, second column. So take the first row, second column. -2 times 1, 0 times 0. Gets me a -2. What about this? This is the first row, third column. Well, that's -2 times 6 plus 0. It's -12. Okay, just to the edge of my paper there. Is that on the, yeah, there we are. Okay. Yeah, and so I'm going to get, it's 3 wide and it's going to be 4 high. Let's go ahead and do 2 more cells. Let's fill in this one and this one. Hey, this one is the 4th row in the first column. Take the 4th row in the first column, 1 times 3 plus 1 times -2. Let's take the 3rd row, second column. 3 times 1 plus 0 gives me a 3. Okay. Anyway, what's the point? If you multiply these two matrices, you get the size. If you take an A by B and a B times C matrix, you end up with a matrix of size A times C. Okay, so that's important to know. How many steps does it take to compute? In terms of A, B, and C, how many multiplications do we need to do? So what is the runtime? What is the time needed to multiply an A by B matrix with a B by C matrix? Well, how many locations do we have in this result?
12.
L.
Yeah, I think I said, I meant to say 12.
12, yeah. In terms of A, B, and C. In terms of A, B, and C. "12 is right. And why 12? It was for how many rows this one had and how many columns that one had. So in general, there's A times C locations. How many multiplications do we need to do for every one of these? Hey, I wanted to know this. Hey, I took one row and one column, and I did that many multiplications. And roughly that many additions as well. Okay. Each needing B multiplications and B additions. Okay. So what is that? ABC is how many multiplications we need to multiply just two matrices. Okay, that's our little background warm up, because the problem we're going to look at or consider is a bigger problem, which is I have like 10 matrices all in a row, and I want to multiply 10 matrices in a row. So what's going to happen if I have 10 matrices in a row? And I'm just going to sketch a picture here. Suppose I have a matrix that is, so it has that example we just had. Okay. And so it is, yeah, the number of rows here needs to equal the number of, the number of columns in this needs to equal the number of rows of the next one. So if I have another matrix here that I'm going to multiply by in front of it, I'm going to need to have width 4, but I might have a 4 by 1. Okay, a 4 by 1 times this is the right shape, it matches up times. So I might have a 4 by 1. Let me do that. Say those in a different color. A 4 by 1. This might be, sorry, a 1 by 4 if you want to say that first dimension first. And this one would be a 1 by 4. This one was a 4 by 2, and this one was a 2 by 3. By the way, when I end up, how big is the answer going to be? So always depend on the last two? No. I'll have to think about that. But here's my question. Notice that if we go ahead and do this one first, we end up with a pretty big intermediate result. We end up with that 4 times 3 array. Okay. But if you're a little bit smart, if you have a little bit of foresight, what can you do? You can say, hey, I'm going to take this 1 by 4 and this one, and when I multiply the 1 by 4 and the 4 by 2, I'm going to end up with a 1 by 2 matrix. And now I just have a tiny little 1 by 2 matrix to multiply against this one. The order in which you choose your matrix multiplications can make a big difference. Okay. So I guess the answer to this whole thing, the answer will always be a 1 by 2 matrix. It's the number of rows in the very first and the number of columns in the very last. That's going to be the size of your overall answer. But the the way you can put parens in here, think I need to do one of these two matrix multiplications first, but if I put my parens here versus putting them over here, it can make a big difference in my running time. Okay, so in this case, it was 1 times 4 times 2, which is orange had 8, 1 by 4 by 2, and then 2 by 3 was 6. It took 14 steps total in the orange. In the purple, where I did this first, this was 4 by 2 by 3, which was 4 by 2 is 8, 8 by 3 is 24. And once I had that, then I had a 1 by 4 by 2, which was 8. 1 by 4 by, what was that old answer? It was a 4 by 3. So 1 by 4 by 3. Okay, yeah, so purple parenthesization took me 36 multiplications, whereas it only took 14 with this. Now, and these arrays are all pretty, so one is like, 2.5 times better than the other. And these are just kind of small examples. If your array sizes are in the hundreds of thousands, okay, which for industrial purposes, they often are, and you're multiplying 10 of them together, yeah, the order, it can be a night and day difference. There might be some combination that lets you do them much better. And when you get more and more of these chained together, by the way, okay, if you have, something like this times, I don't know, whatever. It turns out there's many ways to parenthesize it. You might say, hey, first multiply these 3 together and then do the very last one. Or you could say, hey, multiply, do the first 2, and then do the next 2, and then multiply those 2 blue results. Gosh, there's actually quite a few ways to organize this. Where's my other color of crayon? Oh, back to the orange again. Yeah, so I could take 3 and 1. I could take 2 and 2. I guess I could take 1 and 3. Is that the only? Those are the only combination. Oh, sorry. Within the 3 by 1. Yeah, within the 3 by 1, I also then have out of these 3, there was another sort of choice to be made. Hey, do the first 2 and then the third versus something like that. Okay, so yeah, there's a lot of combinations. You can look up the sequencing, try to compute that as a sum. It turns out a sum that's not easy to get a formula for. In fact, they just call it the Catalan numbers. It arises in a series of things, but including one of the definitions of Catalan numbers, if you go look it up, is number of ways you can multiply a whole series of matrices together. And it's a big number. This grows very quickly. It's exponential, okay? It grows faster than 2 to the n, I think. It's faster than 1.5 to the n. It grows exponentially fast. So if you have 100 matrices to multiply, there are just so many possible ways to do it. You really wish you knew the fastest way, and just looking at all possible combinations and trying to plan out, it can be bad. Okay, lost connection for a bit. Okay, so anyway, there are many ways to chain multiply a whole bunch of matrices together. We're going to use dynamic programming to help find a good way of doing it. Okay, so go ahead and look at this, Dr. Oki's notes. Okay. So I'm going to go ahead and put this page here. And I've already talked about the first part of this, so the chained multiplication. So we're going to multiply a whole bunch of matrices together, okay? And multiplying an ij with a jk takes I times j times k multiplications. Oh, good to know. You get the same answer any of these ways, okay? You can prove that matrix multiplication is associative. No matter how you associate the parentheses, you will get the same answer. Okay. We talked about this, How many parenthesizations are there? So here's an example. And for each one of those, so suppose the side dimensions of the matrix are dimension 0. The first one is dimension 0 by dimension 1. Next is dimension 1 by next dimension 2, dimension 2 by dimension 3, and so on. So yeah, multiplying that A1 by A2 might take this many steps. Multiplying A3 by A4 would be that many steps. And then getting the answer together would be the, gosh, I have a 0, 2, and a 2, 4. So it's going to be 0, 2, 4. Okay, D0. I started with D0. I looked at this one because this gives me a D0 by D2 answer. This gives me a D2 by D4 answer. So, okay. So this third one is the result of doing this multiplication here. Okay, but many other ways to parenthesize. These answers can vary by quite a bit. Okay, number of parenthesizations is at least 2 to the n. In fact, strictly more than, asymptotically bigger than 2 to the n. Okay, I caught a lot of numbers. Okay, we want the best way to do it. We want the fewest number of multiplications. Okay, so we have this here where you're going to multiply n matrices. Each matrix, it has those dimensions. Okay, and so again, it's important to note that if I have a whole chain of matrix multiplications, the size of the result is the number of rows of the first times the number of columns of the last. So the first and the last sort of control the size of the overall product. And we need to know that for when we start feeding into the next multiplication. Okay, so can we figure out how to do it? Well, there's an easy recursive formulation. And here's the key. Here's the one hard part about this, is getting even a basic recursive formula for it, now that we know this. And here's the thing. I'm going to have a function. I'm going to fix my matrices. So A1 through A10, imagine those are constants of my code, just like vals was a constant in the coin problem. It's like, hey, I have these 10 matrices. I want to solve the distance. I'm going to write a function that counts how many multiplications are required to multiply out of A1 through A10. I want to know, hey, if I just were to multiply A3 through A8, how many would that be? I'll call that, hey, I'm going to call my function M of 3, 8. M of 3, 8 is going to be, hey, how long to multiply matrix A sub 3 up through matrix A sub 8. This is my generalization, this formulation. Now that we have this formulation, now we can just sort of crack it. But it's not obvious to say, hey, you want to know what the total number of things is? The helper function will be take any subrange and compute M of ij, number of multiplications for A sub I through A sub j. That's not obvious, okay? Okay. So first of all, a few things to note. M of I is 0. Hey, if I want to multiply matrix A sub 3 up through A sub 3, how many multiplications do I need? None, I'm done. I have A sub 3 right there. Okay, base case. And note that, hey, there is going to be an optimal answer somewhere out of, if I want to multiply, again, I'll make these I and j concrete. I want to multiply A3 up through A8, okay? There should be a dot, dot, dot in this thing here. A3 all the way up through A8. The best way of doing it is just going to be say somewhere where, hey, take A3 to A6 and A7 to A8. Take that break between 6 and 7. Whatever, somewhere there's a breaking point. That's the best place to do the first, to put parentheses. There's going to be a best way to put there's only so many ways to put parentheses, and one of them is going to be tied for, it's going to be best, could be tied for best, but one is going to be best. Okay. And by the way, that if you do divide at point K in between I and J, what is the best? Well, M sub I is going to be the best number. That's the helper function we're going to write. So, hey, take if you want to get 3 through 8, and maybe K is 7, we'll look at, or K is 6, look at multiplying A3 through A6 and A7 through A8. however multiplications those all took time, or then add on the time to do that one last multiplication, which was number of rows of the first one, which was d sub I minus 1, number of columns of the last, which was d sub j, because a sub j, and then their common dimension in the middle was d sub k, the size of the kth, the number of columns of the kth array, or the number of rows of the k plus first array. Yeah, so this is how much I add on to my two subproblems. Does that recursive formula make sense? This formula needs to make sense, and if you think about it, I think is hopefully clear. M of ij, how many multiplications to go from A3 through A8, breaking at k. Well, if I break at k, it's going to be the optimal to go from 3 to k, and then from k to 8, plus the number of time. That gives me the two, that's my two outermost parentheses, plus the time to multiply those two arrays. If these are the best, if m is giving me the best answer, then this will give me, for breaking at k, if I try this for all the different possibilities of k and take the best one, that's going to be here. And that's what this is. Here's the definition of m sub ij. This we can turn straight into code. I'm going to have a function m sub m that takes in two ints, I and j. Again, remember that my arrays, A1, A2, A3 through A8, or whatever, they're all constants. These numbers d, the dimensions of each of those is already pre-computed. It's a constant. It's going to be a global variable sitting up there for the purposes of this. So yeah, my function m of ij, if I is equal to 0, return, or sorry, if I is equal to j, return 0. Else, loop through all k between I and j, and take the smallest out of each of these, making recursive calls. So again, you call m of 3, 7, it's going to call m of 3, 4, m of 3, 5, m of 3, 6. So if I call it m of 3, 7, it's going to call m of 3, 4, m of 4, 7, m of 3, 5, m of 5, 7, m of 3, 6, m of 6, 7. Okay. So yeah, we get all this. Okay, so that's gonna look very much, that's the same code we had in the coins. We had a little loop inside, and we took the fewest so far, the min so far out of all those things. Yeah, this can be the exact same thing. So this is going to be a recursive formula. It's going to be a lot of common calls. By the way, what's our overall answer that we're really concerned about? M of 1, 8. That's the overall solution. Or 110, whatever, however many matrices I had. If I have 10 matrices, m of 110 is the overall answer I want to know. It's the fewest number of multiplies from one, multiply all the matrices between 1 and 10. In doing this, I'm going to break it up into these smaller subproblems. Hey, how many is it to go from m of 3 or A3 through A7? Call m of 3, 7 and find out. A lot of repeated subproblems. M of 110 calls m of 1, at some point it calls m of 1, 4 and m of 4, 10. M of 4, 10 is going to call m of 4, 7 and m of 7, 10. M of 7, 10 or m of 4, 7 is going to get called lots and lots and lots of different ways, get repeated. Hey, let's memoize it, okay? So again, the complexity, we can sort of find out that it's going to be big, exponential, that f to the n, whatever f is. Anyway, so, but I can write that recursive code. Hey, let's go ahead and we have a picture here. So here's this is Dr. Oki's notes. So we get the Ada implementation, okay? And you can sort of look at this. Hey, m from, I want to go from, where's my helper function? Oh, sorry, I need to go back to the notes here to really show this. In fact, I think he has a little picture down lower in here. There we are. Here's the interesting table, okay? We're going to fill in a table where this is going to be, this table location ij holds the result of calling m of ij, okay? So he's saying, by the way, so suppose we have these 5 matrices with these dimensions. Okay, so we can figure out, a 2 times 3 array by a, and then multiply that by a 3 by 5 array, multiply that by a 5 by 2 array, a 2 by, and so on. Okay, so we have this, we can figure out the D dimension of each one of these, just 2, 3, 5, and so on, ending in 3. And now, hey, how many multiplies to get? If you want to multiply array 2 through array 4, turns out we have it filled in here. It's going to be 54. How do we get this 54? Okay, so how do we go ahead and, so he has like, hey, how do you calculate 72? The answer is going to be, in this case, we're going to start with, so first of all, m of ij is going to be if we memoize it, we have 2 inputs. We don't have just, it wasn't like coins of 57. This is going to be m of 2 numbers. And so my memoized array is not just going to be one array from 0 up to 57. It's going to be a 2-dimensional array, okay? Because the input to my function took 2 inputs, I and j. So I have this table going on. So it's a 2-dimensional array. And then how do I compute this? Again, a top-down memoizing would just call, say, hey, what is m of 110? And if m of 110 would start looping through, what is m of 12, 210, m of 12 and m of 310, what is m of 13 and m of 410, what is m of 15 and m of 510, and so on. It would loop through all of those. Those would spawn recursive calls, would go down and go down and go down. Eventually you get to things of calls like, hey, what is, well, eventually it hit base cases like, hey, what is m of 3, we know that's going to be 0. But you might say, hey, what is m of 2, 3? Okay, m of 2, 3 is going to be, hey, I want to multiply matrix 2 through matrix 3. Okay, well, how many things did that take? That's going to be 0. Hey, m of 2, 2, and m of 3, 3 are 0. We're going to add 0 into our answer. We're going to add the thing below it, the number below, the number to the left, and we're going to go ahead and add for 2, 3. We're going to go ahead and add the product of which 2 numbers is it? This is 3, 5, and 2, which I can't highlight very easily. The 3 and the 5 and the 2 are the sizes of this array and that array, and going here. Okay, so which really was the 2 comes from my column row, the 3 d of 2. It's going to come from here, d of 3. The 3 is going to come from here. Is that quite right? I'm a little bit off by 1 somewhere, but okay. Anyway, what's the point? Filling in top down would sort of fill in the table and bubble back up and would end up with the cost of, hey, m of 15 is 78 in this case. Okay. The best you can do it, if you're smart, you can do it in as few as 78 multiplications. Awesome. The top down started trying to compute this. It recurred on, this entire row, each of those, and recurred on other things, and it started filling things in. Eventually we hit the bait cases. If you look at how we could fill it up in a more methodical way, it turns out if we start by keeping track of the diagonal, we know that we can initialize that to 0. Here's how I'm going to fill it bottom up. Remember, we went from a top down, we went from the recursive formula to say memoize, and memoizing was just sort of top down. We just let it call in whatever way it wanted to call. But now we're going to fill up this table bottom up. Here, bottom up means first fill in the diagonal, okay, and then fill in just the thing above the diagonal, okay? It turns out each of those is going to be pretty easy to fill in. I'm going to take, you take the right, you figure out what 2 matrices you're multiplying, you take the product of their 3 dimensions. So I think here, like 2 by 3 by 5 is 30, that's this first 30. 3 by 5 by 2 gives this orange 30. 5 by 2 by 4 gives 40, that's the 40 here. 2 by 4 by 3 gives this one here. Okay, so now we can fill in this diagonal, just above the primary diagonal. Well, once we have that, we can go ahead and fill in these. How are we going to go ahead and fill in these? If I want to multiply, what's the best way to multiply 1 through 3. We'll take the minimum of 1, 2, and 2, 3. Is that the only? Again, with 3, we have sort of 2 interesting ways to multiply. And go about 1, 2, and 2, 3, or we can do 1, 2, and then multiply that result by 3. I'm sorry, that's what we get. Yeah. So, oops, running out of time here. Here he has how to calculate m of 2, 5. It's going to be the minimum of these 3 things here. This is a loop. We're going to loop over 3 other ways to do this. Everything between 2 and 5. We can look at those. And here's the thing to notice is that these other tables, if we're looking at m of 2, 5, hey, m of 2, 2, we're going to have filled in. That's this diagonal. And m of 4, 5 is going to be down here. Everything you want to know is going to already be pre-filled in the table. They're going to be, the 2 numbers are going to be smaller. So they're going to be down below this line here. Okay. So to compute any number, if you know all the sort of diagonals, quote unquote, below it, below and to the left, if you know all those diagonals, you can go ahead and your answer, I think, actually is looking at this plus a little bit plus this versus this plus a little bit versus this plus a little bit. Take the smallest of those 3 to get 72. So, okay. That's where the 72 comes from. Okay. So that's, again, an example of dynamic programming we memoized. Here's a 2-dimensional table. What's the one last thing to mention? Sorry, and then I'll let you go. Hey, how big is this? Suppose we had 1,000 matrices. This is a 1,000 by 1,000. There's a million things in this array. Memoizing is great, but I still have an array with 1,000,000 elements. Can we be smarter? Yeah, all you need to compute a new number is the diagonal that's below it. So to compute the 72, we needed to know this all the numbers on this diagonal, and that's all. In fact, same with the m of 1, 4. Only needed to know this diagonal here. Okay. And once we figure out this diagonal, we can forget this the previous diagonals. Okay. So we start with this diagonal going zeros down the middle, and then we say, hey, after one iteration, we'll get this diagonal, and we can throw away the previous one. After another iteration, we'll get this diagonal, and we can throw away that previous diagonal that had 4 things in it. And then after the next iteration, we'll just keep 2 things. So yeah, what's the memory you need if you had 1,000 by 1,000 arrays? Just keep it the first diagonal, which is 1,000 long. And then on every iteration, you'll actually you can reuse that same array. You'll need less and less of it as you go on, but you only needed 1,000 extra memory locations if you fill out this table in a smart way. So, okay. Whew. That's another example of dynamic programming. Similar, the only difference between the coins problem and this one, to me, as far as dynamic programming, is this is 2-dimensional, and the other one was a 1-dimensional sort of problem. But in both cases, we started with a big array, and we kept only a little sliver of it. For coins, it was a big linear array, and we only kept the last 4. Here it's a big square array, and we only keep 1 diagonal of it. So we keep moving up. So, okay. That is all I have to say about dynamic programming. Okay, sorry for going long. I will see you all on Tuesday. I need to get out some more stuff for you. Have the project to work on, so be looking at that and starting that. And again, the first part is not so bad. Get that first part working, and then go from there. First part is to get a brute force solution working. The brute force is easy to program. So you'll just be figuring out your data structures and reading in IO and printing the stuff, organizing the main functions. Okay, I will see you Thursday. I'll hang around if people have any questions. Otherwise, I'll see you Thursday.